Hey guys, I just want to have a quick chat about the investigation that I assigned in your last class. So, first thing you needed to do was build this circuit in your PHET DC circuit construction kit. So, note that the orientation of the battery looks like this. So the longest line is going to be the positive pole of the battery, and the shortest line is going to be the negative pole. And one way that I remember this is just by noticing that that short line there looks like a negative sign. Okay, so your resistances are supposed to be 5, 10, and 15 ohms, respectively. And what you should have noticed right away for your first observation is that the electrons start moving when the circuit is complete. So let's take a look. There we go. So you should immediately have something like this. And you may notice here that my circuit doesn't actually look very much like the circuit diagram. And that is often the case. The point of a circuit diagram is just to be a representation of the circuit that makes it easy to build. Okay, so it's a very clear, obvious representation of an actual circuit, and makes it easy to see what's going on. That's all. In a real circuit, you're going to have wires all over the place. It's really hard to tell what's going on. Note that if I tap the conventional current button there, that my arrows start moving now clockwise. So this is the direction not of the electrons. In fact, there's nothing really flowing in the case of conventional current, which can be a little confusing. One way to think about it, though, is that conventional current will be the direction of the electric field. Okay, so if you're drawing electric field lines through your conductor, those electric field lines would be in the same direction as conventional current. Okay, so maybe that will help you remember. But nothing is actually moving, though, in the direction of conventional current, which can be pretty confusing for students. It is a convention that we probably shouldn't use anymore, but we still do because all electrical engineering is kind of built on this idea of conventional current. So it is what it is. We just deal with it and don't get too upset about it. That's my advice. Okay, so we have discussed then number one. Next thing we're going to do is add an ammeter and a voltmeter to our simulation. And we just grab these guys here. I've already plugged the ammeter in, so we don't have to worry about that. But note here that my voltage, if I want the voltage to be positive, I need to put the voltmeter in the correct position. Okay, so this is in the positive, from the positive pole, and this black probe here goes on the negative pole. And when I plug those in, I get a value of 9 volts. So when I go back to my worksheet then, I will record my current 0.3 amps. My potential difference is positive 9 volts if I've oriented the voltmeter correctly. Okay, so using Ohm's law, I calculate total resistance, and what I find is that total resistance is equal to 30 ohms. Okay, so then I look at the relationship between total resistance in the series circuit and the initial values of the resistors. And what I find is that my total resistance in the circuit is equal to the resistance of each resistor, the sum of the resistance of each resistor. Okay, so then the relationship for series resistance then, for total series resistance, is R total is equal to the sum of R1 plus R2 plus ... plus R sub n. So for n resistors, this would be our total resistance. Very easy to calculate. Okay, so we then click on wire resistivity and we predict what will happen to current and voltage if wire resistivity is increased. I predict that both values will decrease because I know what I'm talking about. Was my prediction correct? Yes, it was. So according to Kirschoff's law, the sum of voltage in a loop is equal to 0. So what that means is if I go back around here and I take the voltage from my battery and I measure the voltage across this resistor and this resistor and this resistor, and I add all those voltages together, what I should get is a value of 0. Okay. However, if my wires have resistance, then I'm actually adding a third and, sorry, not a third, a fourth and a fifth resistance, okay, or voltage, I guess. These then will consume some of the available voltage. Okay, so let me just draw Kirschoff's law here. So V0 plus V1 plus V2 plus V3 should be equal to 0. And of course, if I add resistance to my wires, then I have to consider those as well. Normally, guys, we ignore the resistance of wires because they're very small, as you will see from some of your problems and handouts. So we don't generally pay attention to them. And in fact, we'll just get rid of these. Okay, but in the real world, they can add up enough to be significant. Okay, so 5. The total resistance of the circuit can be given by using Ohm's law. Do you think, we're looking now at parallel circuits, sorry. Do we think the total resistance in a parallel circuit will increase or decrease? Now, if you look at this, you may be thinking it's more complicated and therefore it's intuitive that resistance is going to increase. Okay, and we will see why that is not the case here in a second. So it will decrease, and I'll explain why in a minute, but my prediction is correct because, again, I know what I'm talking about. So record the total current and potential difference in the circuit. So you should find that your current is equal to 2.7 amps, and your potential difference is equal to 9.00 volts. Okay, so we use Ohm's law, and then we find, and this is weird, we find that our total resistance in the circuit is less than any of our resistors. What? That's weird. Okay, so let's see why. So first, just note that this is the formula that you need to know for total parallel resistance. So the inverse of total resistance is equal to the inverse resistance of resistor 1 plus the inverse resistance of resistor 2 plus blah, blah, blah. And there is the inverse resistance of our final resistor. This will work for any number of resistors. It works the same way. Okay, so record the current through each resistor. We find that our total current is equal to 0.9 amps. And now our total current flowing through the battery is going to be equal to the sum of the current through each parallel component. So what that means, and this is why our total resistance decreases. Each resistor is drawing current as if it's directly connected to the battery. In other words, each resistor, if we measure the voltage across it, should have the same voltage as our battery. Okay, so if we consider that our battery has a voltage of V sub 0, then this will be V sub 1, and this will be V sub 2, and this will be and this will be V sub 3 if we measure them. And what we will find here is that V sub 0 is equal to V sub 1, which is equal to V sub 2, which is equal to V sub 3. Okay? Interesting. Okay, so each of those resistors is going to draw a current, and remember that total resistance will be equal to our voltage divided by current. So every time we add a resistor, our current here is going to increase, and resistance is inversely proportionate to current, as we know from Ohm's law. Okay, so mystery of decreasing resistance solved. This is a pretty important point, so if you feel like you need a little clarification, don't hesitate to contact me. Okay, 9. Build a series circuit using light bulbs. How does changing the voltage affect the brightness of the bulb? Well, brightness is going to increase with increased voltage. Okay, you are supplying more energy to the bulbs, so it makes sense that they would get brighter. Recall that the unit for voltage is energy per charge, or that's not a unit. 1 volt is equal to 1 joule per 1 coulomb. Okay, so if we're increasing the voltage, we are increasing the energy available. Okay, you can't see this, but I just shot a little spittle onto my iPad. That's fantastic. Okay, how could you determine whether or not the light bulbs are ohmic or non-ohmic? The easiest way to do this would be to create a table and vary the voltage and then measure the resultant current for various voltages. And if the resistance is not constant, the bulb is non-ohmic, and it is not. So if we graphed then our data and we put voltage here and current here, what we're going to find is that we get a graph something like this, which you will recall I chatted about in my previous lecture. If we had an ohmic resistor, this would be a straight line, and that is not the case. Light bulbs are a classic non-ohmic resistor, so you need to be aware first and foremost that that is the case. So the first thing you should think of when you hear light bulb is non-ohmic resistor. Okay, next, build a parallel circuit using light bulbs instead of resistors. What happens to the bulb brightness when you increase the wire resistance to the maximum, and why? Okay, so the bulb farthest from the battery is going to be dimmest because our wires consume some of the power involved once they have resistance. If they don't have resistance, then obviously they don't consume any energy. And you may be thinking, well, clearly that's impossible, but it's actually not. Superconductors have zero resistance, but you have to get them very, very, very cold in order for that condition to occur. And physics gets really weird at super low temperatures. Okay, that's about all I have for this handout, guys. So I'm going to stop recording now and have my lunch. Have a great day. I will talk to you later.